Good morning. Welcome to Physics Lab here at Laney. Each week what we're going to be doing is coming into the Physics Lab. We'll be doing some kind of measurements. And so as you can see today, for example, we're going to be doing a series of density measurements of some different metal samples. And so each week when we come in, there'll be a lab outlined with some sort of an objective. And so, everything we do in the lab for the day is geared towards getting the most reliable measurements we can for whatever we've set out to measure for that particular lab exercise. And so for today, let me do that. Let me go kind of through what we're going to be doing for the day, and I think that'll give you a feel for what these lab exercises will be like. So for today, we want to be able to measure density of some different metal samples. Now, the metal samples that we have here, I think what they are, we've got, I think this is brass. So there's a piece of brass that's kind of a cube in shape. And then we have a cylinder that's probably aluminum. It doesn't feel very heavy. It's not very dense. And then we have a block that I think it's just iron. So a couple of cylinders. And then we have a sample of lead. Now I'll be careful with this and I'll wash up really well when I'm handling this. The lead's in kind of a funny shape. If you notice this, it's not a cylinder. The diameter at the top and the diameter at the bottom are a little different. It's what's called a frustum. I think it's one of those volumes that they have you calculate when you're learning how to set up integrals in calculus. In any shape, in any case, those are the shapes that we have to work with, or the volumes that we're going to have to be able to calculate for the day. So taking a look at density itself, now density is defined as the mass divided by the volume. And looking at these samples, they look like they're more or less uniform in nature. So kind of assuming, except for the hooks that are sticking out of them. So those are kind of obvious. We're going to want to come back and talk a little bit about how we want to handle those. And so we want to be able to, we got to be able to measure the mass, and we want to be able to measure the volume. Now there's other ways of measuring the density. We'll see later in the course. We'll get these back out. We'll do some other density measurements using buoyant forces. But for today, we're just going to do a straight measurement of mass and a measurement of volume. So to measure the mass, what we've got are a couple of scales that we have set up here. So I've got a scale set up over here, and I've got another scale set up here. Now these are calibrated from time to time. The scales are pretty reliable in that they report out to plus or minus 0.1 gram. So they're designed to give us a measurement out to that level of precision. Now, what does happen, even if they've been calibrated, there's still a bit of a limit as to, let's just try this and see. So I'm going to take my aluminum sample, my cylinder here, and the scale here is saying 110.3 grams. And so let me take it over to the other, because I have another scale here. Now sometimes students say, but don't you want to keep measuring it with the same scale and for more consistency? But I guess I take a different approach and think, if there's an error, possibility of introducing an error based on these two scales, I want to know if there's a difference of the readings. And so again, if I measure this one more time, I'm getting 110, actually I got 110.2, and then it flipped over to 110.3. Let me try the other scale here. And this is giving me 110.1. Now, it's possible if we recalibrated these that they would be more consistent, but it could also be that we're kind of at the limit of these measuring devices. And so what I'm going to do for the lab today is I think I'm going to measure the samples probably a couple times on one of the scales and then a couple times on the other scale, and then I'll do averaging for the day. So that's probably the best approach I might think of for the day. Okay, because what we want to do is, when we're doing measurements like this, and later on in the course, there'll be times when we just do one measurement and we're done, we measure the mass once. For today, we're going to measure the mass at least 3 times. So I had set up some data tables here. So let's say, oh, it says cube. All right, here's a cube. I think this one's brass. And it says I'm going to do 3 separate trials, or what we call runs. And so I'm going to do 3 runs, and I'll measure the mass each time. And I know that with these scales, it's very likely that we'll get the very same number or something very similar each time. But I want to be able to do some kind of averaging over those numbers. And I want to have an idea of the reliability of the measuring devices. Now, I didn't get units in. I had to go back and write these in. So the mass, that's going to come in terms of grams. And then also for these samples, we're going to have to be able to measure their volume. Now, they look like they're geometric shapes. I've played around with these a little bit. I've tried using these calipers. I've measured the lengths of the different sides of the cube. They seem like they're very, very similar. As far as I can tell, they're identical. So it does look like it's cubic, again, except for that hook that's sticking out. Same thing with the cylinders. I've kind of gone back and forth and measured diameters on these, and they seem to have a consistent diameter. And when I measure the lengths or the heights, that seems to come in pretty similar also. So now, the one exception to this is the lead sample. Lead's a fairly soft metal. If you can see this, you might be able to see that the lead samples actually have been dropped. It's kind of dented on that one side. So that's going to cause us, there's going to be some limitation due to the uncertainty in the length in some of the measurements for the lead. Now, so what we like to do is measure the mass, measure the volume, and then carry out a calculation, take the mass, divide by the volume, and that would give us a value for the density, a measured value for the density of that metal sample. Now, we had talked about with each one of the samples, now this is listed as cube, I think that's just brass, and then there's a couple of cylinders, and for the cylinders, in addition to the mass, we're going to need a height, and we're going to need a diameter measurement. Now, one thing to notice here is that when you write down the formulas, you know, here are the formulas for the volume of a cube, formula for the volume of a cylinder, volume of a frustum. When we write the formulas down, if they're round objects, we tend to write those in terms of radius because mathematically the derivations are more direct in terms of radius. But if I'm in the lab, I'm going to be measuring this as a diameter. And so that's what I've got set up in my data tables, is I have these set up in terms of, well, for the cylinders, I'll be measuring the mass 3 times, probably 4 times. So it's kind of balanced between the 2 scales I have here for the day. And then I'll measure the height 3 times, and I'll measure the diameter 3 times. And then what I'm going to do is I'm going to do some averaging. So the first thing I want to check is to find out, how much variation am I finding from one measurement to the next? So if I set it on these 2 scales, and I did see that there was a little bit of variation between them, but it's probably pretty small. We'll take a closer look at that, but if I've got this cylinder, which is what we looked at, and its measurement of mass is coming in at 110 grams, so it's over 100 grams. If the uncertainty in that is only plus or minus 0.1 or maybe 0.2 grams, that's a pretty small effect. So we've been looking in chapter 1 at percent uncertainty or relative uncertainty, and I think that works out to be like a 1/10% uncertainty in the mass. So typically the scales are not going to be our largest concern in terms of coming up with a precise measurement. And instead what's going to happen is, now I'm using these calipers to get measurements of length, And the way the calipers work, I don't know if you guys have worked with these before, but you can get a couple of 2 or 3 digits of precision, like right now with this brass piece, it looks like it's at about 3.2 centimeters, but there's what's called a Vernet scale that allows me to get one more digit of precision. And so that's what I'm going to do. Now, when I take a look at this, and maybe I better get some lenses here so that I can look at the measuring instrument very carefully. It looks like the best measurement I could write down for this would probably be 3.19. I don't know if you guys can see this, and I'm not going to worry about it so much, but on this scale down here, it's reading out tenths of millimeters. And anyway, it looks like it's 3.19. And so let me get a mass measurement on this too. This is saying 272.2 grams, and my other scale is saying 272. It's actually saying 271.6. So this one's actually reading lower. Okay. So we'll take a look at those measurements and decide how to average over those. So I got a data table for the set up for the cube. The data tables are going to look different for the cylinder. And as we talked about it, I don't have a data table set up for the frustum, for the lead. But the frustum's going to look kind of like this data table, but it's going to have 2 columns for the 2 different diameters. So that's how that will differ. Now, I did want to take a look at the brass because what I was measuring earlier was a mass of 271.2 grams. Now that was from the scale over here on the right. If I really am truly accurate to plus or minus 0.1 gram, that would give me a relative uncertainty of 0.037%. Now that's well below 1% uncertainty. And what we're going to kind of find out during this semester, during lab, is that most of the measurements that we look at, we're hoping to keep the uncertainties, the relative uncertainties, to within 1%. That becomes kind of a goal that we have each week coming in. And again, it seems like with the scales, even though they're not agreeing right to the tenth of a gram, they're pretty reliable in terms of, you know, they're within, well within 1% of uncertainty. So even if I find out that this number is quite a bit higher, maybe it's plus or minus 0.4 or 0.5, that's still going to be, you know, only a couple tenths of a percent of uncertainty introduced by the uncertainty in the scales. Now with the length, what I just read off was 3.19 centimeters for the cube, plus or minus 0.01 centimeters. Now that works out in terms of relative uncertainty to be about 0.3%. Now, playing around with these calipers, what I found is I can't reliably make the measurements to within 0.01 centimeter. Sometimes the variations in the measurement from one measurement to the next, they get larger. And so, again, these are kind of idealized numbers, but it could easily be that this amount is, it could be the uncertainty or the limitation in the calipers is twice that amount, or maybe 3 times the amount. And then I have to look at my formulas. So mass, there's one factor of mass, there's one factor of volume, but within the volume are 3 factors of length. And what we find is, if the measurement of length has an uncertainty of 0.3%, when I cube that number, the number goes up, the uncertainty goes up by a factor of 3. So multiplying by, every time we multiply by a factor, so this is kind of like saying, for the cube, there's a mass divided by L times L times L. Well, the mass has a relative uncertainty, 0.037%. The lengths, each one has an uncertainty of 0.3, so when I combine the 0.3 plus 0.3 plus 0.3 to get an estimate, I'm going to find out that that is getting pretty close to being the 1% uncertainty. Okay, so the uncertainties could get that large. So I just wanted to point that out. So data table, gotta have units, make sure you got units. Now I'm going to be doing the measurements here in the lab and providing, I'm going to be running through the labs and collecting data and providing that to go along with the videos. Here's an example of a results table. So these were data tables, here's a results table. Once I've got all the data figured out, I've got formulas written down, I'm showing how I'm carrying out the calculations. Then what I can do is list the samples that I have and then write down the overall best estimate for the density that we've found for the day. And then compare that with accepted numbers. Now, accepted values are going to come out of some kind of a standard textbook. So you could look in your textbook and see if there are accepted values there. You could also go online and see if you find accepted values, look up the densities of different metals. I'm sure you're going to find some tables online that have lists of different metals, and then they list the accepted value for that particular metal. Now what does happen is it could turn out that the samples that we've been given to do these measurements, the samples we've been given, maybe they've been manufactured differently. So our aluminum, for example, it's unusual to have a pure sample of aluminum. More likely we have some kind of an alloy. And so even when we look up accepted values, one of the things we have to keep in mind is, well, this is what the book says is the accepted value for brass, but I know brass is an alloy, and some brass has different composition than other brass samples. So we're going to have to think in terms of how do we want to, what do we want to report in terms of the uncertainty. So it could be that, I guess what this all comes down to is our numbers could be different just because the samples are different. And that's not an error. That's not something that went wrong with our measurements. It's just saying that when we very, very carefully went through and measured everything and calculated a density for this material, it could be pretty reliable, again, within 1% or 2. And it could be the stuff we're looking online is just measurements that were made with a different alloy. So something to keep in mind. I think that's it for the day. So I think I'll show, probably show a couple more examples of carrying out the measurements and showing how the data is going to be collected. But it really comes down to taking each of the samples, doing at least 3 runs. So, and again, I might do a 4th run here. So 3 or 4 runs. So I'll measure the mass, and then I'll measure the length those 3 or 4 times. Now what does it mean to say 3 or 4 measurements that are independent? What that would mean in terms of mass is, I could set it on this scale and see what number it comes up with, 271.2, and then I can remove it, and then I can place it back on. So I want to remove it away from the measuring device entirely, and it did give the same 271.2, and 271.6. So 271, and let me try this at 270, this is 271, right? Yeah, so this one is actually lower. This one's reading a little higher. I think I had that reversed before. So I'll probably take a couple measurements from here, a couple measurements from here. So there'll probably be 4 of those. And then with the calipers, same idea. What I have to do with the calipers is I am going to be taking each of these measurements, I'm going to take some lengths, some heights, some diameters, and very carefully read right down to, as best I can, down to that 1/10 of a millimeter limit on the calipers. And then I open the calipers up, set them down, set the sample down, pick it back up again, and do an independent measurement. So, in science, we're always trying to catch any errors that we might be making. So rather than try to get a set of measurements that are very, very, let's say, consistent. So sometimes what will happen in lab is students will say, well, we're going to have the same person do that measurement all 4 times to make sure that there's better consistency. But, it probably makes more sense if we're trying to catch a possible error to have different people do the measurements. So if we can have different people taking the measurements, then we can take a look at the numbers and quickly make a quick determination. First of all, are the numbers all within kind of the range we would expect? Or are there some numbers that just don't make any sense? Because we may want to, we may find out that somebody just read the number wrong, or some kind of an easy error got made, and that's why we're double checking the numbers as we go through. So don't hesitate to have more people take a look at the measurements and then talk about it. Discuss, well, what happened here. It looks like maybe your numbers are a little different from the rest of the group, and then find out how the measurements were done. Again, what we're trying to do is make sure that everything stays as accurate as possible. So data tables, results table, let's talk a little bit about lab reports. So the way lab reports are going to work in the physics classes here is that you are going to, you're going to be writing up lab reports. There's always that boundary between how much of this needs to be independent and how much of it is working together. And you can kind of work together all the way through all of the measurements, all of the calculations, double check each other, make sure that you're being very careful, stop by office hours, and ask whatever questions at all you need to understand what's going on. I mean, I'm everybody's lab partner in some sense. So for the lab reports, when you write these up, they really should be written up independently. So you should be writing up your own lab report, and writing up the lab report, that's part of the course, is writing all this stuff up. Now the format that I'm going to suggest is to start out with the title and the objective. And that shouldn't be too difficult. What will happen each week is that we'll have a title and we'll have an objective. So I'm gonna write those on the board. Those are all going to be on the board. They're going to be written right up there. You're welcome to just use the title and objective that I've provided. If you want to put a little more detail into the title and objective, that's fine, but I'm perfectly fine with just the title and objective as written. Now, I think the format that I prefer personally is once you've written down the title and objective, go ahead and get the results. What that does for the reader, which is probably me, is that you've stated what you set out to do, right? Here is my objective for the day. This is what I got. So I set out to measure densities of some metal samples. Here are my metal samples, and here are the densities that I measured. Now, the reason I prefer that is because once people can see your results, then what they can do is they can start to formulate questions. I wonder how the results turned out to be this. And then as they read through, this is, again, my personal preference, as they read through your report, then they can start to see how you came about, how those numbers came about. So you don't have to do that if you want to put the results table at the end instead. I know that that's a common format also. Now, in addition to the results table, I do want, maybe a sentence or two, just a comment of what happened in terms of the results. So, and a very common example of what you might write would be something like, all of the densities were within 2% of accepted values, something like that. Or you could say, all of the densities that we measured came within 1 or 2% of accepted values, except for the aluminum. And the aluminum was actually 6% higher than accepted, possibly a different alloy, something like that. Sometimes what students do in a lab report too is they'll, at this point, they'll say something like, yes, the lab was a success because we got whatever numbers. So a couple things to keep in mind here. Typically, in lab reports, typically you don't state it was a success or not a success. I guess that's the other alternative here. That's not something you have to concern yourself with so much as take a look at the results. The results table will have percent differences written in. And so whatever the percent differences are, maybe make a comment on that. Just comment on how large the percent differences were and what you think about why you might be seeing that difference. Another thing that I want to encourage students to think about is I always worry that students in their science classes have been taught that you're rewarded if you get the answer that the teacher wants you to get, but you're penalized if you don't get the numbers. And that too isn't really the way science works. So the way science works is, we do the best, most careful measurements we can. We carry out the calculations, we double check, triple check the numbers, and then once we've got the numbers, we just report those. So we're not trying to match numbers up with an accepted value. Now, accepted values can be useful to possibly catch some crazy answer we've ended up with. If we're off by a factor of 2 or 5 or 10 or something, then usually it's a units error or something like that. But in any case, think in terms of we just want to do the most careful numbers, and then we'll see what our results turn out to be. So now the results table, I guess we talked about percent difference here. I should give a formula. So for percent difference, what I'm going to say for purposes of this class is use this. Percent difference is taking the measured value, subtracting off the accepted value, dividing by the accepted value, and then multiplying that by 100%. So the way this is read then is it's read as the numbers we got are this many percent different from the accepted value. Now again, remember the accepted value might not even be the same alloy or the same substance, but we are going to do the measurements relative to accepted. It's a useful measure to work from. Now, if I multiply that number, when I divide through, this is like a percent difference. When I divide through, the units go away, and so there are no units on a percent difference. And then I've multiplied the number by 100%. Now 100% is just the same thing as 1, so that doesn't change the numbers. So, maybe I find out this is at 1.2. Maybe the brass I measure, and this works out to be 1.2% higher than accepted values. Maybe the aluminum turns out to be 3.7% lower. Go ahead and leave the plus and minus signs in there. That's fine. So plus and minus signs, if everything's coming out plus, it means that all of our densities are larger than the accepted values. If they're minus signs, then those show that we got numbers that are below what the accepted values are. All right, we've talked about this. So title and objective, results table, data tables. Now I make a big deal about units because units are really important. And then formulas. So any formulas that you've used in any of the calculations, those should appear in the report. So you should have the formulas. You don't have to show all the calculations. If you want to show a sample calculation, that's fine. If you want to show all the calculations, you could do that too. But in any case, make sure that the formulas are included. Now, it lists data tables and graphs. Today we don't have any graphs. Most weeks we will have a graph or two that you have to complete. So the data tables and the graphs, they need to be clearly formatted. If I've got graphs, I have to make sure that I'm labeling the vertical axes and the horizontal axes of the graph with the correct units, with the correct physical quantities. Everything needs to be labeled properly. And then finally, the lab report, limitations. This usually goes by the name of error analysis. So now in error analysis, again, this kind of comes back to the idea of what were the measuring devices that we used and what were their limitations. So I've written that down, like the direct measurements for this lab. The direct measurements are coming from the scales. And when I first wrote this up on the board, I was thinking the scales, more often the scales are within 1/10 of a gram of each other, but today, for whatever reason, they're not. We're going to have to boost that up. I'm seeing differences of like 0.4 or 0.5 grams. That's quite a bit larger. The calipers, ideally, we could measure those right down to plus or minus 1/10 of a millimeter, but it's not really that practical. So I boosted that up to 0.2, and even that's, we'll see. We'll see if we can really get the calipers measuring this accurately. So first of all, think in terms of the direct measuring devices that you have, and plus or minus how much in terms of units. Now, the other thing that should go into the limitations or into the error analysis are possible assumptions that we've made. Now, in today's lab, certainly one of the assumptions that we've made is we've kind of neglected the hooks. Now, I could take the hooks out, I guess, and do the measurements. Maybe I'll do that. When I've got a class full of students here working on this, I usually encourage them not to take these out because the threads are very delicate and they could get damaged. But maybe I will try pulling out the hooks today and redo the measurements with the hooks out. In the past, I've done that, and the hooks are less than a gram, I think. I'm going to take one out right now and see. We'll see. I'm being very careful. I don't want to break this. The hooks are needed for some other, we do a number of different property materials on these samples. Our metal samples, you know. All right, so this came in at 0.9 grams. So this hook that's sticking out, I guess if we put this on here, 270.8. So now we have those, we have an empty place inside there, right? So we'll see. I'll have to decide which way I want to go ahead and take the measurements. When I do collect the data, I've got my paper, my notebook set up right here, so I can come in and start taking some data. All right. So those are the kind of things that you can include in the error analysis. You can include something about what assumptions are we making, and we've, you can say that we've neglected the effect on the hooks. All right. Now the lab reports are officially due 1 week after the lab. So by the time the next lab is starting, or the official start date for the lab, they're going to be due. Now these should show up on Canvas, so you should be able to go to Canvas and take a look at the due dates, which come up, and the due date should be listed there. But in general, it's the week after. Now, in the lab itself, you're going to need to be able to carry out all the calculations. My policy typically in lab is before you can leave the lab, your lab group, you and your lab group, have to show me that you've taken all of the measurements, you've carried out the calculations, you've double checked, you know all of the units that apply, and that you have roughed out the data tables and the results table. So everything's calculated. The idea is that when you go home from lab, The only thing left to do is write up that lab report. Okay. So, questions on any of this? If you guys have questions on any of the stuff for today's lab, let me know. And again, stop by office hours and let's get any questions that you guys have, let's get those answered. I think we've looked at everything in a fair amount of detail. I've gone over the scales, we've looked at the calipers, so I think we'll just wrap things up right there. Again, any questions, stop by office hours.